Hi everyone, welcome to Random Thoughts with Alex. A few weeks ago, the world discovered Object 3I Atlas, the third known interstellar meteor or comet. The other two, both discovered in the last decade, are 1I Oumuamua and 2I Borisov. All three objects had a perihelion fairly close to the Sun. Oumuamua came as close as a quarter of an astronomical unit. Borisov approached to slightly over 2 astronomical units from the Sun, and Atlas will approach to about 1.36 astronomical units from the Sun. So far, we have never found an interstellar object that stayed further from the Sun than Borisov, even though we have the technology to do so. Statistically speaking, there should be far more objects that stay further away from the Sun, say from 2 to 5 astronomical units, than objects that come closer to the Sun. Why haven't we found one? That's what I would like to discuss in this video. To discuss this, we will need some data. We will generate this data with some computer simulations. I developed a simulation model that calculates the trajectory of any number of objects approaching the Sun. Then, it calculates the trajectory closest to the Sun in higher resolution and calculates the perihelion from that. We compare the perihelion with the lateral distance to the Sun when the object is outside the gravitational pull of the Sun. That object could have been anywhere on a circle defined by that lateral distance, so the expected number of objects at that distance is proportional to the radius of that circle. Based on that information, we can calculate the distribution of interstellar objects in relation to their perihelion. By integration, we can calculate the relative number of objects that approach to within a certain distance from the Sun. If we also know the initial velocity and the number density of objects in interstellar space, then we can calculate the average number of interstellar objects per unit time in relation to the range of perihelia. Spoiler alert, in my final analysis, the number density that closely matches the three objects that we've observed over the past 8 years is roughly 0.00125 per cubic astronomical unit. That means in every cubic volume of interstellar space of 1 astronomical unit wide, 1 high and 1 deep, there are on average 0.00125 objects the size of Oumuamua or larger. That is, 1 object every 800 cubic astronomical units. Imagine a cube with a side that reaches from the Sun to Saturn. 1 object in that cube. Now, I started with a number density of 0.003, and I will show the preliminary results with that number. Here you see some of the code that I wrote in GNU Octave to simulate the trajectory of interstellar objects near the Sun. I won't discuss the code, I will just run it. What you see in the chart on the top right is the trajectory of 5 interstellar objects at different lateral distances from the Sun. The little dot here represents the Sun. We see that the first object comes very close to the Sun and almost makes a complete U-turn. The further away from the Sun, the wider the curve of the trajectory. On the bottom left, we see the distance of each object to the Sun as a function of time. On the bottom right, we see something similar, but accounting for the distance the object still has to travel to its closest point to the Sun. It's the lateral distance to the Sun. This chart shows you the degree to which the Sun pulls objects closer relative to its original trajectory. As a result of this effect, there is an accumulation of objects straying close to the Sun. We need to account for this if we want to calculate the distribution of interstellar objects according to their closest approach to the Sun. Next, we assume that, far from the Sun, every trajectory is equally probable, and based on that, we can calculate the distribution we are interested in. Let's start with objects that move with the interstellar speed of Oumuamua, 26.33 kilometers per second. That is 5.55 astronomical units per year. In this Excel file, we pretend that every interstellar object moves with that speed. We focus on the chart here at the bottom. It shows how many objects per year we should see coming closer to the Sun than the value on the x-axis. From the chart, it appears that we should see an object with a perihelion of 1/4 astronomical unit or less once every 40 years approximately. In other words, finding Oumuamua so quickly was quite a fluke. Let's move on to Borisov. The chart indicates that we should see an object this close to the Sun or closer every 2 years. Borisov is a comet. Its visibility was quite strong. We should see an object like this with a perihelion of 5 astronomical units or less twice per year. That's within the orbit of Jupiter. There should have been 16 such objects since we've spotted Oumuamua. Why haven't we seen them? We'll get back to that question. Third, there is Atlas. Because of its high speed, it covers more space, so we should see more objects like this. We expect an object like this once every 3 years, and about 3 objects per year within the orbit of Jupiter. But so far, we assumed that all interstellar objects move at the same speed, which is not realistic. We need to estimate the velocity distribution of interstellar objects and incorporate that into our calculations. I found a paper from 2021 on arXiv by Marshall Eubanks and co-workers that gives a velocity distribution of stars, and they propose that interstellar objects will follow a similar distribution. What I find interesting in this chart is that it has a fat tail at the high velocity end. These are stars that move faster than the escape velocity of the Milky Way. In other words, in 100 million years, none of these stars will be in the Milky Way anymore. Why are there so many of them? The Angry Astronaut has made videos about that phenomena that you might find interesting. He speculates that some of these stars are ejected on purpose because they will explode in violent supernovas and destroy the neighboring stellar systems if they are not removed. I came up with my own velocity distribution function that follows the one in the paper fairly closely, with exception of the fat tail. The agreement is very good for the most part. When I incorporate this in my calculations, I find the distribution over here. Because there are a lot of fast objects in interstellar space and they cover more space, this increases the frequency of interstellar visits. We find that there should be about 7 such objects approaching closer than Borisov per decade, which is more than what we've seen. Now, if we decrease the number of objects in interstellar space, the number density to 0.00125 per astronomical unit, we find that about 3 objects per decade should come within the trajectory of Borisov per decade as what we've seen. Now there are 2 issues we should discuss. One is that there should be more fast objects in what we've seen. Maybe it's a coincidence that we haven't seen more fast objects. Fast objects are harder to discover, so maybe we just missed them. The second issue is potentially more serious. We should see about 13 objects per decade within the orbit of Jupiter. We've seen only 3. We haven't seen anything that stayed further from the Sun than Borisov. We should have seen about 10. Maybe they just weren't bright enough. After all, there are more small objects than big objects, and the smaller ones are only visible if they come close enough to the Sun. But for now, it's an anomaly. The Vera Rubin Observatory, which came online recently, will systematically search the sky for this kind of objects. In the next decade, this observatory will give us the data to resolve the issue of the missing interstellar objects. Most likely, it will find that we just didn't look carefully enough to see these missing objects further from the Sun and the missing fast objects. But if the Vera Rubin Observatory doesn't find those objects, we have to ask ourselves why. Is it possible that we find a disproportionate number of interstellar objects close to the Sun because they have been sent there? After all, there are some remarkable coincidences surrounding Oumuamua and Atlas. It's a wild speculation at this point. The Vera Rubin Observatory will either debunk this speculation in the next decade or confirm it. Either way, the perihelion distribution of interstellar objects, surprisingly enough, is actually one of the most exciting things to follow up on as the results from the Vera Rubin Observatory come in. There it is. I hope you liked this video. If you do, please click like and subscribe, and I will see you in the next video.